Hello and welcome to Calculus 2, the first lecture of the semester, which is area between two curves. But before we go and take a look at area between two curves, how about we take a look at the area under a single curve, which is something you learned, hopefully, in Calc 1 in 5.2, when you learn to solve definite integral to calculate area under the curve. So if I have, let's say, function f of x, square root of, let's say, 3x, and I want to take a look area under the curve from 1 to 2. We can graph and understand this by graphing our function square root of 3x on xy coordinate system, and then taking this little piece between 1 and 2, which is the piece that we want to know the area of. So now, what we need to do is to integrate, because integrals calculate accumulation. They calculate the amount, the area. Derivatives subtract, integrals add. They are opposite operations, which is why you had that fundamental theorem of calculus that had derivatives and integrals cancel each other out, because they are completely opposite. So anytime when you want to accumulate amounts or calculate areas, or let's say energy under, right, it will be area under the curve, energy in physics. So we will set this problem as area equals integral 1 to 2 of square root of 3x dx. So this is something you hopefully learned in Calculus 1. And this tells you that the area is obtained by the formula integral a to b of whatever the function f of x is times dx. So this is, again, in 5.2, here it is, Calc 1, right? So Calculus 1, this is the formula to find area under the curve. However, your function f of x is not allowed to dip below x-axis, because it will create negative area, and then the net area and all of this will be different. But we'll get there when we need it. So now, once we know that area is simply obtained by integrating the function between two x values a and b, we can set up our integral here. So now I need to integrate this. Now, integral of 3x is not a basic function. So you can either use u substitution, or you can be clever with algebra and avoid the issue of area under the curve by kicking the constant outside, because square root of ab in algebra is the square root of a times square root of b. So we can split these two, split this function into two separate, right, and then kick square root of 3 outside of the integral because it's a constant. Now the trick is to rewrite square root of x as x to the 1/2 using algebra. And this is where the formula from Calculus 1 integration, right, kicks in, where we know that the integral of x to the n dx, whatever exponent you have, is x to the n plus 1 divided by n plus 1 plus some constant c. By the way, this constant c is not there for decoration. We need it. so make sure. Trigger my allergies, and then I start acting erratically. So we integrate by adding 1 to a half, which is 3 halves. So the answer over here is square root of 3 x to the 3 halves divided by 3 halves, and now we are computing from 1 to 2. So this vertical line means compute. So this works out to be 2 root 3 over 3 when you work out the double fraction. And now you have 2 raised to the 3 halves minus 1 raised to the 3 halves, and that is some number which is equal to the area. So we calculated the area under the curve. If you are, interested in decimals, you can punch this into a calculator and get a number. So this is 2 root 3 over 3 times 2 to the 3 halves minus 1. 3 halves in a calculator, you can use 1.5 obviously as the exponent, and then subtract 1 times the mess over there will get you a number. So when you have a function and you have two x values that will break that function to the left and to the right, you are able to calculate the area under that curve. Sometimes, right, you can use geometry to bypass calculations. If you're integrating under the straight line, could be a triangle or a trapezoid. If you're calculating area under the curve, the constant line, well, obviously it's a rectangle underneath, so it's easy. But if you have a curve, right, something that it's not easy to deal with geometry, you can always use this method to calculate. So that was the Calculus 1 review of area under a single curve, where we utilized definite integral from 5.2 to calculate. So now, today's lecture is on area between two curves. Say you have y equals x, and let's say y equals 4 minus x squared. And you would like to know the area here. Now, I'm not going to go into the reason why you want to know something like that. The idea is just you want to know. So we'll start there. So what is the area of this piece? Well, how would we calculate something like this, right? So before we go and solve this problem, we have to take a look at the theoretical setup so that we can understand and learn the formula that will help us set this problem up. So we'll come back to this problem. I am going to leave some space. I don't need much. And over here, I'm going to go into this theoretical piece where I have two arbitrary functions. Let's say I have something like this and something like that, let's say. And I would like to find out the area between these two. So the function on top I'm going to call f of x. The function on the bottom I'm going to call g of x. So that's our standard way to denote functions on x and the y. So first off, we see that to the left and to the right, functions go as far as these two intersections, which will give me A and B values on x-axis. Are we all bueno with this? Excellent. So you can even drop these verticals down into A and B. So that's where this shape is the fattest, right, between A and B. It's clearly skinnier the higher you go. So you will always look for the fattest area, the length, I mean, and that will be your A and B. Now those are your A and B, which are the limits on the integral. And you will find those A and B when you set f of x equal to g of x, because setting f of x and g of x, you see that they share the y and x value, right? The point at which these two functions, where they intersect, is the point that it's shared. So here, I'll write this in blood. To find A and B, we set f of x equal to g of x. So this is the first thing you have to do if the functions intersect, right? If the functions intersect, then the points of intersection will give you A and B. Now, sure, if someone comes along and say, well, I want just this piece over here, well, then they gave you the point at which the cutoff is. You still have to calculate A on your own. So that's the easy part. Set two functions equal to each other to calculate A and B. Guys, those are the A and B on the integral, right? That will go on the limits. All right, so now next order of business is to figure out the formula for integration. Now at this point, let's think of a banana. If you hate bananas, have two. Maybe you like them eventually. What do you do with a banana? When you buy a banana, you get the unit that has the peel and the banana inside that you eat, right? What do? You are holding in your hand the entire banana, you peel, and you throw away the peel, and you eat only the edible part, right? So think about this. What I'm going to do is I'm going to set up the integral from a to b of f of x dx. Now that is pretty much like the entire banana, because I have all of this calculated as area with that integral, right? It's just area under the curve. I have the piece that I want, which is the top piece, and the piece that I don't want, which is the piece on the bottom. Same like banana. You have a banana and a peel. The piece you want and the piece you don't want. And then I'm going to subtract the peel, a to b, of g of x dx. Now that one will only calculate the part that I don't want. So if I have everything, and then, hold on. Much better. So the first integral calculates everything in there. The second integral is going to take away what you don't want. What's left? Exactly the piece you want, right? Now, if you remember a formula from Calculus 1, it says that if both integrals are in terms of dx, and both integrals have the same a and b, you can mush them into one integral, which is the property of linearity. So this can be combined into a single integral of f minus g dx, which is your formula. So now we write that the formula for area between two curves is f of x minus g of x dx. This is the first formula that you are memorizing in Calculus 2. This is going to be the area between two curves where f of x is on top and g of x is on the bottom. So top minus bottom. And you guys have your first formula to calculate things. So now, armed with this formula, I'm going to go back to the problem I have up there and calculate see? So now I know to find a and b, I set x equal to 4 minus x squared. Now, this is going to be x squared plus x minus 4 equal to 0. To put this in the form of a quadratic polynomial that I can work with. Since this is not factorable, boo-ha, right? We are going to use quadratic formula, let's say, to find the intersection point. Please note that a is equal to 0. I did not shade all the way on the other end to include the other intersection, right? There is an intersection here. But I'm not asking for this at all. So my a is not going to be at this intersection here. My a is at 0 because I only want 0 to the second intersection, right? So this is where my a is, and my b is here. So my integral is 0 to something, the way I shaded. I could have shaded just the other side, and it will be a to 0, or shade everything, a to b. So it depends what you want. So we're going to calculate a and b, but we are only going to use b, because a is 0, the way I shaded. So we use quadratic formula. That's going to be what? Does anyone remember? Negative b.
Plus or minus.
Great.
Square root minus 4ac over 2a.
Beautiful. Your a is 1, your b is 1, your c is negative 4. We are talking about our algebra now. So negative b plus minus square root of b squared minus 4 times a times c divided by 2a. 2 times 1 is 1. 2 times 1 is 2. So the whole thing over here is negative 1 plus minus square root of, this is 17 over 2. Yeah.
Where are you getting
Negative, it's a negative b, right? B is 1.
Oh, okay.
So when you plug in, right, from here, a is 1, b is 1, and c is negative 4.
Mm-hmm.
So we feed those into the equation. So there's our limit. And clearly the one with the plus is b, and one with the minus is a, because that would generate the negative number. So our integral here is 0 to negative 1 plus root 17 over 2. Can't be more annoying. Top minus bottom. Top function is the 4 minus x squared minus the bottom function, which is x dx. So I'll give you some colors over here. So this over here is your f, and this is minus g. So g is on the bottom. That's the linear one. So that's just x. And then the quadratic polynomial on top. Great. So now we integrate each one of these. That's going to be 4x minus x cubed over 3 minus x squared over 2 computed from 0 to negative 1 plus root 17 over 2 equals to some number. When you compute this, you just plug the values in. The goal of this course is not to learn to compute. You should know that from Calc 1. The goal is to learn the formula, to set it up, and then we use basic integration in this case. 4 becomes 4x. X squared plus 1 is x cubed over 3, using the formula we reviewed earlier, right here. Right? It's n plus 1 over n plus 1. And then you have a single x, that's x to the first power. X to the first power, 1 plus 1 is 2, divided by 2. Then you take this mess, plug it in for x, then you take the mess, plug it in for x and there, and then you square them and cube them and write them, whatever. You can actually come up with a single decimal here, and then plug that decimal for these numbers. Minus 0, and we get some kind of number. That's 6.2. I hope you're not disappointed. Welcome to Calc 2. I know, right? What happens if the functions are sideways? Well, we have the dy version of this integral as well. So let's take a look at another version of this, which will have a sideways function, because you love it so much. Say you have this configuration. I missed. Now I gotta do it all over again. There we go. It's ugly now. Whatever. So let's say you want the whole piece over here. And this point here is at 7,1. So now you have a sideways parabola. Those of you who paid attention in a pre-calculus course know that when parabola goes this way, it's y equal x squared. When parabola goes that way, it's x equals y squared. And it's not a function. So now, we would like to solve that problem. It's some kind of mechanical part. We need to know the area. Yes?
Don't you not want the part on the left side of the y-axis?
Why?
Don't you have to then include that as a negative?
Okay, great question. The answer is that these don't care about it because you are looking at the difference of 2. So if you have 2 in the negative, the difference is still the same. So if one function goes below x-axis and the other function goes below x-axis, and you take them together and shift them up, the difference between them is still the same. So what you're asking about applies only for a single function, which is why I didn't want to dwell on it too much, because it doesn't apply for two functions, because two functions care about the difference, not because. But that was a great question. Cool. I know you have a pulse. Thank you. All right. So now I have to figure out the equations. Well, clearly this one is y equal x, same as before. Now, if you recall the function y equals a x minus h squared plus k, which was the one that looks like this, then the one that is sideways better be x equals a y minus k squared plus h, right? And that's for the one that is sideways. Like this. Now, looking at what I have my value for h and k over here. So x-axis, but in here, it opens up towards negative x-axis. So it should be negative. So what I have in this case to generate this function, hello pre-calculus, right? We have x equals negative, and now you have your y minus k. That will be y minus k, k is 1, squared, plus, and then the value over here is 7. And now you can work that out, which is negative y squared minus 2y plus 1 plus 7. Apply the negative everywhere. Negative y squared plus 2y plus 6, because the negative makes that positive 1 into a negative 1. And we have our formula. Now, most of the time that formula is given. But just in case it's not, you can also figure it out. Good. So now I have something that will require dy integral, which is the sideways integral. And if there is justice in the world, which never is, c to d f of y minus g of y dy. This would be the formula for the sideways calculations. And now, instead of having top minus bottom, like we had before, you have right minus left. So what is the area for this problem? Oh, I did not calculate C and D yet. Limits C and D. Set f of y equal to g of y. So f of y is the one that is further out. G of y is the one that is closer in. So f of y we already got. That's negative y squared plus 2y plus 6. The other side, g of y, is just y. Because this side is y equal x. So if you're going to write it x equals y or y equals x, right, you pick whichever one you need. So we move y to the other side, it becomes negative y squared plus y plus 6 equal to 0, and then hit it by negative 1 to get y squared minus y minus 6 equals 0. Now this one we can factor. Y minus 3, y plus 2 equals 0, from where we get y is 3 and y is negative 2. Those are your limits C and D. Because I'm going to go up now to the picture. Negative 2, oops. This is the intersection, and this is the intersection. This intersection gives me negative 2, and this intersection gives me positive 3. Those are your values because we are looking, right, where this object is the fattest. It's the fattest between this line here and this line here. Those are your bottom and top, which are your C and D, which is why it's negative 2 and positive 3 on the y-axis. There will be something that I will scream many times in this class, but let me just finish this and then I will scream that. We have negative 2 to 3, and then we have right minus left. So to the right, you have the parabola, which is negative y squared plus y plus 6, and then minus y in parentheses times dy. So the first three are your f of y minus this one over here is your g of y.
Actually, that's 2y.
Oh, it's 2y? Yes, thank you. Y. I was just testing and you just passed. So very good, very good. I was just wondering who was paying attention. So plus 5. All right, so now we simplify this. We can combine those y's. Negative y squared plus y plus 6 dy. And now we are ready to integrate. Negative y cubed over 3 plus y squared over 2 plus 6y from negative 2 to 3. Now I'm tempted to write equals a number, but let's solve at least one of these. All right. So plug in 3, we get negative 27 over 3 minus plus 9 over 2 plus 18. So that's when I plug in 3 in each of the y's. And then we have minus, and now I'm supposed to plug in negative 2 in each one of these. Negative 2 cubed is negative 8, and a negative is becoming positive 8 over 3. And then I have negative will be squared, so I have 4 divided by 2 is 2, so plus 2, and then minus 12.
It should be minus 8. Because cube.
Yeah, but you have a minus here, and then this minus. So when you cube a minus, it becomes minus 8, and then you have a minus in front, it's a positive. Now this minus is the subtraction of the integration. So it becomes a positive 8 in this case. So this is negative 9 plus 9 over 2 plus 18 minus 8 over 3 minus 10 plus 10, because this is negative 10 and the minus in front, plus 10. That's 9 and 10, that's a 1, and 19. So that's 19 plus 9 halves minus 8 thirds. Common denominator for this mess is 6. Now 6 times 19, that's 6 times 20, 120, right? And minus 6, 120 minus 6 is 114. Plus 9 times 3 is 27 minus 16, right? Let's say it's good enough. So 114 minus 11 divided by 6 to give us 103 divided by 6. It's not even, it's not, so can't be simplified. There you go. 103 divided by 6. Now, you can divide this using a calculator and get a decimal, and then if you care, carefully graph this and literally count the squares. And it has to come up to be the same. It's one of my Calculus 1 projects. I give you a parabola that it's upside down, and I ask you what's the area, and then you have to graph that parabola on a square paper and count the squares underneath. It has to work out. Let's say you have a linear line at 3, and you want to know the area from 2 to 5. So what's the area from 2 to 5? 9. Why? Because you know that the height is 3, and then the width is 3, and 3 times 3 equals 9. No calculus necessary, right? Of course, you can flex, because it's calculus. You can go 2 to 5, and then you're integrating a 3 dx, obviously, right? You get 3x from 2 to 5, which is 15, minus 6, which is 9. Let's say you're tutoring a kid, right? And you say, oh yeah, 3 times 3 is 9, and the kid goes, why? There you go. How else do you describe why water goes downhill, right? But if you, I don't know if you thought about it, but let me zoom in. How many squares do we have? We have 9 squares, right? If each one of these tick marks here is a unit, and it is, because this is where your 2 is, and your 3, and your 4, and your 5, then this square over here is 1 by 1, which has area of 1. And then you have these areas, and you have 9 of these ones. So that's all 9 units. So if you want to check our previous problem, right? You graph this carefully, and the amount of squares that it's going to take, now obviously you'll have to do some fitting because they are not following the edges, it's not Minecraft. You are going to have all of these fit in to be exactly the fraction you have. So that's a nice little project. So 6.2 calculates area between two curves, whether those curves are on top of each other, in which case you will use dx, or sideways, in which case you will use dy. Now, you might ask, well, how do I know which one to use? Because the homework is just going to dump a whole bunch of problems and just say find the area. And no one tells you use dx or dy. This is where the representative rectangle, dx or dy, plays a role. And this is probably the most important technique that you need to learn to set things up in Calc 2, but then even more important in Calc 3 when you go into 3 dimensions. So I'm going to draw the problem we just had. Doesn't have to be exact. And I'm going to attempt solving this problem using dx. We just saw the solution using dy, so we know dy is the way to go. But let's say we are just, playing around. Look what happens. If you draw delta x representative rectangle, now I hope you remember what representative rectangle is. In 5.1 in Calculus 1, you learned that to approximate area under the curve, you cut the shape into these rectangles. And then you calculated area of each one of these, you added them up, and you came up with the approximation. And then we said that the thinner these rectangles are, right, the thinner they are, the less error you are going to have. Meaning that if you fit infinitely many, infinitely thin rectangles inside, you will have exact area. Now that infinitely thin, we call representative rectangle with the width dx. Very, very, very thin rectangle, infinitely thin. So, if I draw one of those representative rectangles dx, guys, when you write your function f of x dx, you are calculating area because this represents your height and this represents the width of the rectangle in question. It's f of x times dx. All right? So this dx is not optional. Yeah, I don't have to write it. You do, because that's the width. You cannot claim that the area of the rectangle is a equals a. No, it's a times b. This dx is actually this b in the area for the rectangle. So we're not messing with that. So now, this dx is actually the width of this, and look at the height. Goes from one function to another function. Right? So if I have this right, like this, and I draw my representative rectangle dx here, you see that the height is riding f of x function, and the bottom is riding g of x function. So f on the top minus g on the bottom gives me the height of the rectangle, and times delta x for the width of the rectangle. And then I add infinitely many of them, which is what integral sign means. Summation, add all of them. So do we understand this, hopefully? So the height is f minus g, and then times the width, which is dx. And then you put integral in front to add all the other ones that are there, because this is not the only one. You have infinitely many of them. So that's what the integral sign is for. Now, what happens, I'm going to kill this because I don't want it to. What happens if you are doing the wrong thing over there? Well, you still have a top minus bottom. But as this dx walks over here, which function is it touching on top? F, right? And which function is touching on the bottom? F again, right? Do we see it's a problem? So it was not a problem here because it was touching two different functions. Not a problem. But as soon as it passes this line, dx is touching the same function on top and the bottom. And that's how you know you can't use it. Because what's f minus f? And what's 0 times dx? 0. So you are not going to get any value for this entire area. It's just all dead, right? Now, let's do it right. If I go and I put a dy representative rectangle, no matter where you draw dy representative rectangle, this side of the representative rectangle always rides the linear line, and this side always rides the parabola. So it's always going to be f minus g, and you are not going to get f minus f or g minus g to get a 0 and kill the entire area. It's always going to be f minus g to have height, and then times dy, the width, you will always have the area. So something like this, you actually have to, guys, you have to sit and you have to study this stuff. It's not enough to see it here and, you know, you're good to go for the exam in a month. No, right? You have to sit, you have to think about these things, and you have to make these combinations, and the homework will provide you with a lot of exercises to practice these combinations, and you will see that you know, by drawing these dx and dy, you will know which way to go. So the book will have a lot of examples, and next Wednesday is when we have the next class. So I hope that you will spend a lot of time in sections 4.9, 5.2, and 5.5 reviewing basics of integration, including the much needed 5.5 U sub that will solve 90% of the problems on the first 2 exams. Okay? So we don't really want to mess with something that is that frequent, right? Next time we will start with reviewing obviously U sub, and next Wednesday we have next 2 sections, 6.3 and 6.4. If you want to read ahead, that'd be great, and we'll go from there.